A 1,500 kilogram car is towed, starting from rest. The figure below shows the tension force in the tow rope as the car travels from x equals 0 meters to x equals 200 meters. What is the car's speed after being pulled 200 meters? Neglect air resistance and rolling friction. So in this situation, we can see that we're given the mass of the vehicle, and we know that we're starting from rest, which is our initial velocity, and we're looking at the tension force that's being applied over a distance, and we want to know the car's speed. So if we know the tension force over a distance, that is telling us about work, and if we want to know about the car's speed, we'll be able to find that from a change in kinetic energy. So in this situation, we see that our motion is in the x direction, and that the tension, we're given the x component of the tension. We can assume that the tension is fully horizontal, and this is just the value of the tension. But one way or the other, it's the x component. It's already projected in the direction of our motion. And we've said that the work done is the force in a given direction times the displacement in a given direction. But this was only for a constant force. When our force is not constant, we see that the tension is changing. We can only use, we basically have to assume a tiny bit of work that's done over a tiny distance, and that we can assume that the force is constant over this tiny distance. In order to find the total amount of work, we have to integrate both sides. If we integrate dW, we get the full value of W. The full value of the work is the integral of the force with the displacement. More specifically, in this case, the work would be the x component of the tension times dx, the motion in the x direction. If we have an integral like this, we can find it directly by finding the area under the curve. The value of this integral is the same as the area under the curve. We can see geometrically that that's a triangle. The area of a triangle is 1/2 the base times the height. In this case, the base is 200 meters, and the height is 500 newtons. And so the work done is 50,000 joules, or 50 kilojoules. This work being done is going into the kinetic energy of the car. This force of tension is the only work we need to look at, because gravity and normal force are both vertical and thus are perpendicular to the motion, and we're neglecting any other possible horizontal forces. We're told to neglect friction and air resistance, etc. So this work done is our change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. In this case, we're told that initially we're at rest, and so the initial kinetic energy must be 0. Here we have 50,000 joules of work that's being done. That energy is being transferred to the car. It's going to show up in the car's kinetic energy. And so we can find the velocity that the car must have. And we find that the velocity must be 8.16 meters per second, or really 8.2 meters per second. Now we solved this entire problem looking geometrically at the force as a function of position, and we did our integral by finding the area under the curve, treating this as a triangle. But we can also find it directly by doing the integral. Looking at this curve, we see that it's a straight line. We see that the rise is 5,000 and the run is 2,000, or 200 I should say. And so the slope is negative 25 newtons per meter. We can also see that the y-intercept is 5,000 newtons. Thus, the equation of this line is negative 25x plus 5,000. If we want to do the integral, we're going to integrate the force with respect to position, which in this case is now thus. We're integrating across dx, we're integrating across the range of positions, which is 0 to 200 in this case. When we integrate, we'll evaluate at our two endpoints. We can see here that when we plug in 0, everything is going to go to 0, and so this value won't really matter for us. But when we want to find the work done, and we get 500,000 joules. This is why it's always good to check yourself, because I see over here I used 500 joules instead of 5,000 joules, and so I ended up with 50,000 joules instead of 500,000 joules. When we take our new value, our correct value, and we end up with the velocity is 25.82 meters per second. Again, using sig figs, we can simplify that to say that the velocity is 26 meters per second.